Thanks for joining us. My name is Wyatt Gorman. I am a high-performance computing specialist with Google Cloud. I'm based in New York City. Thanks for joining us at Technical Deep Dive into Storage for High-Performance Computing. Just quick show of hands. How many people know what high-performance computing is, what kind of workloads there are, and then keep them up? And how many people are actually users of HPC, or researchers, or engineers, or sysadmins, or managed teams? Okay, great. It's about half. Excellent. So we have, please, first of all, if you have any questions up front or throughout the talk, please put them on our new Dory. It's an internal system that we've had for a long time that's really helpful for just submitting questions that you might want to ask and easily going through them. So we have a great lineup of speakers today. Again, I'm Wyatt. I have with me Dean from Google Cloud, as well as Sven and Minh from Data Direct Networks. And I'll let them tell you a little bit about what they're doing with Google Cloud and the marketplace. But first, I just want to talk about what HPC is, for those of you who don't know, aren't familiar with it. So just some examples of some industries that HPC users are in that really is fundamental to their industry. Manufacturing, so computer-aided design, chip design, things like this. Life sciences in terms of genomics, financial services, climate modeling, everything like that, right? So as you might know, for those of you who do HPC, in these industries, compute is the real driver, right? So all the time, questions are getting bigger, right? Demands for compute are growing. And so we see this especially in the top 500 supercomputers. So this is a graph of the growth of those systems in flops, which is floating point operations per second. And so you can see that we've grown now and exceeded in total capacity an exaflop of storage, performance, I'm sorry. And we're going to see the first exascale system very shortly, around 2021. So all of this compute and also storage is constantly growing. So if you look at the last 10 years of storage growth, we started in 2008 with about 3 petabytes on the largest system, Roadrunner, at Los Alamos. That was about 55 gigabytes a second, which was pretty impressive for the time. But in just 10 years, we've 83x'd the capacity to 250 petabytes in a single storage system and gone up to 2.5 terabytes a second, which is absolutely tremendous, the factors of scaling that we're seeing, not only in compute, but also in storage. And so all of these things together, combining compute, combining storage, and software, of course, drives your mission, right? It's not just about infrastructure. It's really about your science and what you're trying to do. So a great example of that is the Broad Institute. The Broad Institute is a genomics research organization and genomics sequencing organization, a partnership with MIT and Harvard and others. And so these guys were able to, using Google Cloud and the massive amount of compute that they have, get the price of processing a single genome down to under $5, which is really tremendous for making genome sequencing accessible to the world and letting you do things like 23andMe and so on. And so when you think about what it takes to actually do this work, it really costs, first of all, a lot of money. So that's why you saw national laboratories owned these systems. To build these systems at a massive scale is really a huge undertaking, not only in infrastructure, but also hardware and buildings and maintenance and everything like that. But it's also very difficult to run these systems efficiently, right? So you can see on the right a graph of typical utilization in a system, and blue is the total capacity of your system, where the red is jobs. And so at a time of very high utilization, you have users sitting in the queue waiting for their jobs to run, waiting for other jobs to complete. And on the right, you can see times when there aren't enough jobs and you're just wasting money running your supercomputer. And so this is a problem even within Google, but we've gotten really, really good at bin packing, which is a term used in HPC, which basically means just utilizing your resources very efficiently, right? And so that's all driven by Borg, and so we'll talk a little bit about how we do this in Google Cloud. And so to avoid having to deal with all of this on your own system, on-prem, you can really very easily turn to Google Cloud for all of our very easy fast provisioning, our security, and our storage, which we'll be talking about a little bit more. And so another user that decided that it would probably be a good idea to turn to Google was Twitter. And so you'll probably hear at our keynotes this week that Twitter moved 300 petabytes of data to Google Cloud storage. And they used Google Cloud and decided on Google Cloud because of all the reasons that I just showed you in terms of faster provisioning, flexibility, and security. So in terms of infrastructure and what it actually takes to run HPC, very quickly before we dive deeper into the HPC storage, you really need three things. That's compute, storage, and networking, right? So if we look at compute, the fundamental driver of compute in Google Cloud is the Google Compute Engine. And so Compute Engine is really designed to be powerful and flexible for your workloads. So we have up to 416 CPUs in a single machine, 12 terabytes of RAM, which you just heard about this week. We have Intel Optane and local SSDs, which we'll talk about in a little bit. But we also have something that's very key to HPC workloads called custom machine types. And so this is a way that you can size your instance, choosing very specifically the number of CPUs and RAM that you want to perfectly fit every workload that you run on Google Compute Engine, right? So if you have one system that needs 12 terabytes of RAM and 400 CPUs and GPUs, right, you can do that. If you need one that needs 12 CPUs and 12 gigabytes of RAM, you can build one. We also have compute-optimized VMs, which are super high-speed CPU machines, great for HPC. We have GPUs, of course, so we have NVIDIA K80s all the way through T4s, as well as TPUs, which are awesome for machine learning use cases. Preemptible VMs are an awesome tool for running checkpointed and quickly running code. So they are up to 80% off of a standard instance. However, they live for a maximum of 24 hours and can get preempted anytime within that 24 hours with 30 seconds of notice, right? So again, checkpointed jobs like genomics sequencing, where a single job within a batch of jobs can fail and be restarted, is perfect for preemptible VMs. And then at the instance level, networking scales in terms of bandwidth at 2 gigabits per second per vCPU up to 16 gigabits per second per vCPU. And we support 15,000 VMs per VPC. Right, so that's a lot of instances on a single network. If you need more than that, let me know. And speaking of networking, in terms of the global network that you need for massive collaboration and massive data storage, we have exactly that. So we've invested billions of dollars into our network. And when you think about a global network, you have to think about laying undersea cables and dealing with things like shark attacks, which sharks like the electromagnetic signals coming off of the wires. I don't know why, but so we have a shark-proof network. Just one benefit. And then finally, in terms of compute storage, we have a wide array of local compute storage options in terms of not only Google Cloud Storage for object storage, but also persistent disk, local storage like local SSD, and then file store and other solutions that we'll be talking about just in a little bit. So to talk about HPC storage in Google Cloud at a larger scale, I'd like to introduce Dean.
Great. Thanks, Wyatt. So what I wanted to talk a little bit about is, all right, now we're thinking about doing HPC in the cloud. In many cases, users already have an HPC infrastructure, like a compute, Linux cluster or a supercomputer or something in their existing premise. They're not just coming to this, like brand new, but in a lot of cases that can happen too. So what you end up with is a series of on-premise data centers, each with their own cluster, and then connected into a variety of Google Cloud regions. And so the trick then is, how do we get data into the regions and back again? And then once we have the region up and running, how do we tailor make, I like to say, the compute side and the storage side for the workload that you're trying to run? So some of the common models that we're seeing from a variety of HPC users boils down into three categories. One of them is what I like to call launch, which is you're running maybe MATLAB or some smaller program on your laptop or on a desktop somewhere, and you're not using a lot of compute because it's just a single machine or a couple machines, but then you want to dynamically burst your job into the cloud. And so there are partners that can enable that, where you're using 2 cores here, let's say, and you burst out to 200 something, and it becomes a very dynamic, real-time type bursting scenario. Good for bursting compute, not so good for bursting storage, because if you're trying to do this in real time, you're going to wait for that data transfer to end up happening while you're trying to dynamically burst. The one that I see a little more common is the burst by type, I like to say, which is essentially taking the workloads that are running on-premise and splitting them up into a set of categories. And so 2 categories might be the HPC high-performance type workloads that require super low latency networks and use MPI and a variety of those kinds of tools. And then separating that out from the HTC, so the high throughput computing, which is more, embarrassingly parallel type jobs or ensembles in some communities where they're running just millions of smaller jobs on the system. And so what you can do is then, leave the on-premise system that you have, optimize that for one set of jobs, let's say the HPC type jobs, and then burst the rest into the cloud and have the data stored permanently up in the cloud. And so you're really sort of bifurcating your data plane, but as well as your jobs. And then that way, that enables you to optimize, instead of having to optimize on-premise for every workload, small IOPS and big bandwidth jobs, you can really separate and target each one individually. And then the last one, of course, is all-in, which is obviously, awesome and removes, the hassle of trying to do data movement back and forth. But, I think that's more of a process, right, in terms of getting there all the way to that phase. All right. So on the storage side, then, what you end up with is an on-premise data center that probably has your Linux cluster running and your own storage system. And then you have a set of file systems that you might want to target inside the cloud. So here, just as an example, I have our Google Cloud File Store, and then we have a Lustre system in the system. And so first, you can see that we can tailor make the compute side of each of these clusters to whatever the workload is, right? So file store is a smaller, NFS-based offering, so you'd have a smaller set of nodes that would be accessing that with whatever, number of CPUs that they require, and tailor making then the storage and file store for whatever that is, whatever the requirements are. And then we have the other one as well on the larger compute cluster that you're going to have, and then targeting a Lustre system that's optimized for whatever the workload is, right? High bandwidth, high IOPS, or whatever is needed. And then the challenge becomes is how do you get the data back and forth, right? And so a lot of cases, people are using cloud storage in the middle for that data transfer because it provides the secure and high bandwidth pipe that you basically need in order to get the data up. And then from cloud storage, you can then essentially burst out into your file systems. And then the results can then flow back the other way as needed. So talking a little bit about our cloud storage offering, I think most of you might already know about it, but essentially it can be used for a variety of different purposes. You can use it as your production, HPC storage offering, or you can also just use it as a cold tier, right? And store essentially the cold data in your system and save money by keeping it there. Or you can just use it as, again, a transitory place to copy data in and out as data's flowing back and forth from your on-premise system. And so cloud storage is obviously awesome, and it can do amazing things, and it can scale across the globe. But in many cases, what you end up with is still your applications are not written for that. And if you're writing applications for on-premise supercomputers or Linux clusters, you probably are not writing applications for object storage, in which case you end up with needing some sort of file storage. And so, I asked this question, well, what do you mean file systems in the cloud? Like, we're going to modernize, right? This old file system stuff, POSIX is from, 50 years ago. Like, why are we there? But the thing is many, as I said, many HPC workflows that are running today rely on a POSIX-based file system. They rely on the performance, and they also rely on the types of behaviors that file storage can support, such as in-place updates, handling large numbers of small files, because they deliver latencies that are sub-millisecond versus the much tens of milliseconds, right, that cloud storage provides. And the other thing that I like to remind people is that file is actually very cloud friendly. You know, NFS as a concept is built into Linux, and it's available from every VM that you launch, and it's a core part of the Kubernetes infrastructure. And you can dynamically use NFS and Kubernetes just without doing any work whatsoever. And so it's also very friendly to preemptible VMs, which is another core part of HPC, as Wyatt brought up. And, you know, obviously very familiar, right? All of us understand what file is. We do this on our laptops every day. These are the apps that, you know, we were learned to write in university. And so, you know, it's just something that becomes a very natural transition. So what I wanted to do then is go into some of the details that, okay, so you're going to use the cloud, you're going to deploy a larger file system inside the cloud, going through some of the just general bare bones ways on how GCP works in terms of compute and storage. So at the top there, we have our compute VMs. And so, you know, something, you know, as Wyatt said, we need to choose the right number of eCPUs, or if you're GPUs or TPUs, or whatever the infrastructure you need for your compute layer. But then these nodes are also your file system client, right? Whether it's NFS or a POSIX-based client such as Lustre. And so you need to make sure that it has the bandwidth it needs. And so at the 2 gigabits per vCPU, you always need to make sure that you have enough of those to at least deliver the network performance. Even if you didn't need them, you know, you're going to need them for the network, I'm sure. So the next step then is the storage servers. So these file system clients are then, you know, using some level of distributed I/O across a set of storage servers that you're going to launch, right? And these end up being VMs inside of Google Cloud as well. So you need to keep the same things in mind. The one is the networking, right? There's no point in putting up a whole bunch of small VMs in many cases. You're going to want to have the largest network capacity possible. So you're going to want to think about at least, you know, again, 8 cores for those servers. And you might then want to think about, well, does the file system support some level of extra caching where we could put in some local SSDs? How much RAM do we want to support? And all of that can be configurable depending on the type of job that you're using. So then finally, there's going to be some storage, what would be the point of the file system. And so, you know, if you're going to store this data durably, you're going to be using persistent disk. And then there's a few things that you need to watch out there for as well. And so one of them is that the performance scales linearly with capacity. So, you know, you can look at your capacity requirements, and then you have to look at your performance requirements. And then you need to choose the capacity, provision the capacity that meets both of those. So, you know, some people don't like paying for extra capacity if you're not going to use it, but don't think of it that way, right? Think about it as you're paying for performance. And, you know, some of that is just logical, right? I mean, if you can't have, the more capacity it has, the more spindles or the more SSDs you're engaging, which means then you have, you know, enables more bandwidth and IOPS to the system, right? So that it works very similarly onto how on-premise systems work. The other thing to remember is that with PD SSD, there is a set of vCPU requirements, and that's because the high IOP rates of using SSDs just drives cores. And so it's a tiered system, but you get the best performance with using 32 vCPUs at that level. And then the other thing is to remember is that they scale linearly, but then they hit different limits at different capacities. And so it's easier just to choose the largest capacity, and then, you know, you don't have to worry about whether or not you could somehow have eked out performance. But some of the common mistakes I've seen is where they choose smaller VMs and smaller capacities, and then they have a lot of them. And it's just a lot easier to shrink the number of VMs and storage servers that you're deploying and maximize out the bandwidth and the IOPS of each of them. All right, so we have a lot of storage options in Google, and it can be quite confusing in terms of figuring out which ones are, you know, right for you. The top row here is the structured storage options, which I always like to put up, but you know, we're focusing in on the bottom ones today. And so we talked a little bit about cloud storage and persistent disk, and I'll mention file store briefly. But then we also have a set of HPC storage partners that we're partnering with and are putting up different levels of file systems inside of Google that are really targeted towards these HPC use cases. So the first one to talk about is Google's own file store. So this is great for small to medium-sized jobs. Like I said, maybe a MATLAB job or some sort of smaller and test system that you're running. And it's fully managed and NFS-based from Google. Next, if you need to go bigger than that, Elastifile is putting up a fully managed NFS-based ScaleLoad file system that really is targeted as the next tier of file store and delivers a really great number of IOPS. So if you have a high IOP workload, then this is a great choice. And of course, we have our NetApp Cloud Volume Service. And so with them, you get all the performance that you normally expect out of using NetApp on-premise, but you get it with all of the integration and the ease of use of GCP. And so it's just like the other two. It's fully integrated into the console and the billing system, and you could just dynamically use it as if you were using any of the other storage options in Google. And so we are also developing now a partnership with DDN around their Lustre service and their other software storage offerings. And so now I'm going to pass it off to Sven from DDN to talk about that.
Hello, my name is Sven Oehme. I'm the Chief Research Officer for DDN. With me is Minh, one of our senior software developers. Let me swip to the next slide. So since this week, we actually announced on the marketplace a new offering. DDN acquired last year WemCloud, which was Intel's division that was running the Lustre development organization. So DDN now essentially owns the majority of all Lustre developers worldwide. So we brought a service online. Minh was instrumental in actually get this up and running. And while I'm speaking and talking over the next slides, I'm going to pass it over to Minh for a second. He's going to start a demo to show you how easy it actually is to deploy this on Google Cloud. And while basically the deployment in the background is running, I'm going to talk about the rest of the slides. Thanks.
Thanks, Sven. So the Lustre solution, the easiest place to find is on the marketplace. So we just need to search for Lustre. Okay. And here is our offering. Lustre on GCP, and as you see, it's similar to any other offering. So when we launch, keep in mind that this solution is on multiple instances, so you may want to plan ahead of time. But we do provide step-by-step and predefined profile for you to just launch is the easiest. So all you need is a couple of steps. So the deployment name is already pre-filled. If you have one deploy already, it will change this deployment name to a different one. The zone, you can select your zone, and the network, by default, it just pick whatever network that's your zone in. One thing that you might want to consider is using the private Lustre network that you're choosing. So for this demo, I am going just a range. And for the, if you want to access directly to your cluster from outside, you can just pick external IP, automatically allocate for you, or you can just, you can select none, and it will create a router so that you can have a gateway to jump into before you go into your cluster. File system name, you can change it. Here is something that we have predefined a couple profile to help new user or user have different level of need. So quick start is pretty small, standard plus, and premium. For today's demo, I am going to just select the premium, and it also can be a capacity base where each profile have a minimum requirement for capacity. So if you want to increase more than that, you just enter here. And step 4, if you don't select any profile on step 3, you can go into step 4 and make change to your server any way you want. Some people, they want to, tailor to the way that they want to be a certain server, a certain memory. You can do all that customization here. The last step is select number of client include into this deploy. So for our purpose, I pick 8 client, and the last step is just click deploy. And the deployment approximately on this deploy is about 4 minutes. So while we waiting for the deployment, I will hand that back to Sven, and we'll come back to here, and once it complete in about 4 or 5 minutes, and we'll continue.
Yeah, thanks a lot, Minh. So a couple of things to mention is probably there is a default 8x5 support associated with the service. So you can actually pick up the phone and call somebody if there's a problem. It is not fully managed yet. We're looking for feedback from customers if they also want a fully managed service of that. And then we're gonna look into this. So if you deploy the system, as Minh said, this is probably gonna take somewhere around 4 minutes. We also deployed large systems of hundreds of terabytes in size, and everything is basically a matter of a couple of minutes to get deployed. So it's actually is pretty easy and pretty scalable if you need a very large amount of capacity in the cloud. So let's talk a little bit more about Lustre and what DDN is actually bringing to the table here. So DDN's Lustre is the number world parallel file system deployed. We have a large number of AI customers, so we're not just playing in HPC. We have very specific offerings in the AI space as well. And the whole purpose of Lustre is really to provide very, very high performance where traditional file serving solutions typically lack in. So while you can do a lot of things with NFS and SMB with normal workloads, as soon as you get to a massive amount of parallelism, they're typically not really your choice of workloads. So we have some customers today deployed in the world. If you look at like the top 500 supercomputing list, massive amount of them are actually running the Lustre file system inside. So there's a very interesting performance benchmark called IO500. I'm talking a little bit more about that. And what you see here is essentially demonstrates the capabilities of that offering. So we have customers that have millions or billions of files. We can do hundreds of gigabytes, even terabytes per second throughput with this technology. It's something that is really provenly deployed in many, many sites. So we basically try to bring this on-prem technology that we deploy in many, many sites today in the cloud to give customers the choice to not just run this on-prem, but also get a very, very nice cloud experience with a very proven technology that is deployed in many of these areas today. So the things that primarily differentiates Lustre from some of these other options that you see on the marketplace is really superiority and scalability. As I just said, deploying hundreds of millions, even billions of files, petabyte-sized systems. We have some systems on-prem today that are 3 digits petabytes in size. So we know that the technology scales, so you can deploy this in the cloud with the same technology. The other nice thing is that you can very nicely scale it for various types of workloads. It doesn't matter if you have massive random read performance workloads, or you have massively sequential workloads for reads or for writes, or you have small files or large files. There is lots of options that you can have. We try to keep it as simple as possible. That's why we have all these profiles where you can basically pre-select from. But if you need something that is highly tailored for your environment, you can do this with the offering as well. And what a lot of people don't know is many AI workloads particularly, and we really put lots of effort in this area, rely under the cover on MMAP. So many libraries, LMDB and multiple others, use MMAP under the cover. Many other file system options actually have significant performance scaling issues with that. And so we put lots of investment into this area to make this very, very fast. So we believe that's why this option is very interesting, particularly if you try to run AI workloads in the cloud, because with a distributed file system that has optimizations for that, a lot of the frameworks that basically get shipped out of the box on these systems are going to run significantly faster if they leverage MMAP under the cover. We also have, given the size of the deployments we already had, there's lots of expertise in the organization to manage massively scalable systems. We actually run for lots of customers very massively scaled systems on site. So we provide these extra services to customers on-prem. And basically with the service offering and the knowledge that we have in this area, we try to bring all of that into the cloud as well. And we're more than happy to also have separate engagements in specialized services for that if there are very specific needs you have. So the technology is heavily being worked on. We try to tailor, as I said, this offering specifically for cloud. There's lots of powerful tools that we are in the process of launching in subsequent releases that are going to come over the next couple of quarters. So you have today already capabilities to set quota allocation in the system. You can either do this by subdirectory, there's options you can do this by user or by group. And we're going to add significant management capabilities in terms of pooling. So you have much more fine-grained control as an end user or based on data that the system automatically collects in terms of file heat and being able to basically manage data placement across multiple pools of different types of storage inside the system at basically with the full automatism and the tools required for the end users to manage that. We also have a capability for doing very fast transfers from on-prem to cloud, because it's great if you have an offering on the cloud or if you have an offering on the prem, but if you can't figure out how to make the movement for these very, very large-scale systems working, you need more than that, and we have a special product which I have one extra slide for that. And there's auditing capabilities as well that is required, obviously, for lots of customers for governance purposes, and we have lots of security features into this solution as well, so you can do things like secure mounts where people only can mount certain subdirectories of the system without other people essentially seeing the data of each other, so you can basically separate each other's out in the file system namespace. IO 500, as I said, that is a benchmark that is used trying to provide basically a very fair comparison between different storage solutions in the market out there. We've done a couple of tests in the IO 500 benchmark with Lustre. This is just one example of what we deployed. We basically deployed 120 client system, 120 server system with 180 terabyte capacity in total. We achieved 107 gigabytes per second throughput on the system, and we basically showed absolute linear scalability going from the smallest configuration we've tested all the way up. And as Minh already mentioned, and what we're going to show in the demo in a few seconds is that all of this was launched essentially and executed in a couple of minutes. These are the results of the benchmarks. So we did different tests. So we scaled servers independently of client. So this is essentially the Lustre server count scaling. So you see the IO 500 score, how it basically goes up when we add servers. I have to mention one point, the benchmark itself is very complicated. So as larger you make the benchmark data size, as more complex its execution is. And so as higher you go basically in the scores, as tougher it's going to be if you increase the scale of the system. And we also, as I said, increased the gigabytes per second essentially by just adding individual nodes into the system. So here you see the scale basically going from 10 servers to 60 servers to 120 servers. And you see basically a very nice scale of that performance in the system. And we believe if you just add more nodes into the system, it's just basically going to run faster and faster as more resources you add into this. So the nice thing is, as I said, you can scale capacity completely independent from metadata and independent of the IOPS or throughput in the system. So basically whatever metrics you try to achieve is just basically a matter of picking the right input for the deployment, and we can basically meet all of those needs. So two more slides that are very specific. I said this is our cloud offering. Lots of our customers already have on-prem offering, or customers that have a cloud offering also need an on-prem offering. So I want to show you two slides of what we deploy today on-prem. So we just launched a new product. It's called SFA 18K. It's essentially the fastest storage controller for file systems that you can purchase right now. It's essentially a 4U device that delivers 80 gigabytes per second throughput over the network. And this is essentially embedded running the same Lustre file system software that we deploy on GCP. So if you're looking for an offering that needs to be deployed on-prem, this is a very, very good offering for that. And the second slide that I wanted to show you is a product called Dataflow. So this is the one that essentially ties this on-prem technology with the cloud technology, or also cloud to cloud, or also cloud or on-prem to on-prem. So the product's called Dataflow, and what Dataflow essentially does, it tightly integrates with multiple storage sources and targets. So it is not actually limited to just Lustre on-prem and Lustre on the cloud. It has targets to NFS, it has targets to SMB, it has targets to IBM Spectrum Scale file system, it has targets to multiple different sources and targets including S3, and even has support for tape. And what differentiates this technology from other simple file movement or data management solutions is that it's particularly built for massive scale. So you can basically take a 100 petabyte file system as a source and a hundreds of terabytes or petabytes file system in the cloud, and you can basically fan out the data movement across large number of nodes and large number of networks. So instead of running on a single node, it's essentially going to send a request to the source system. You specify with rules what data you want to be moved. It finds this data very fast with built-in technologies in that technology if it's supported. So for example, if you run this against a Spectrum Scale cluster from IBM, it's going to use the policy engine that is built in there. It's going to find the files very quickly that you select, then splits the workload across large number of workloads and transfers them in parallel into the cloud. Because that's one of the big challenges with this massive data movements. How do you move that data between cloud and on-prem? And you can't really do this from a single node. You need a massively distributed system in order to do that. And basically, Dataflow is providing you exactly that capability to move between all these different technologies.
Okay, so this was the screen last we left. When it finished deploy approximately 4 to 5 minutes on this particular profile. So as you can see, on the right-hand side, you see some information. What we provide is a web console that you can see file, you can see your statistic, or you can see status of your Lustre file system. So, so this will display the network, the Lustre network, file system name, also the NID, the network LNet NID that you use. If you have new client bringing in to mount, that is the mount point that you want to use. So all information is there, and we are running the latest version of Lustre 2.12.0 and the CentOS 7.6. And below here is the information that you can automatically, we have automate the way that you can introduce new cluster, a new client into mounting the same file system. So you can read all that. But one interesting I want to show you is that if you visit the console, you will see a file system, Lustre file system, and you see metadata, and you see the target, the object storage target that we just allocate, and the total file system. Just for this demo, I just launched 25 terabyte with using a few minutes, and the cluster here are showing the OSS, which is each server, and we are using approximately 10 OSS. And on the right-hand side are these read and write. Right now, I think it's doing the read. What I just did was I launched an IOR program on client to demonstrate, the disk activity. So you can see as the disk is reading at 400 megabytes per second right now. And if we go to the graph, including the ganglia graph, you can monitor the statistic for last hour or day or week. So you have metadata server, management server, and OSS. So I'm going to show you so we have 10 OSS. The first default screen is going to be the low of OSS. As you can see, the low just spike up because we just launched a IOR test. One of the interesting things, you can see a lot of statistics create, write, read for individual OST if you want to look at it, but we'll look at the total byte, read and write total on all of them, and they do a stack graph with 10 different colors. And you can see, if you click on individual one, you can actually see, everything CPU, low luster. Let me see. We can collab and we can look at the OST matrix. All the statistics is there for you to look. And while you run your application, you can actually see the low, everything. So I think that.
Yeah. So as you can see, there's lots of detailed information that we expose, so it's very easy to also find potential bottlenecks where you might actually be limited by, like if you know exactly what the network limit is of the individual instance, you know that when you deploy a larger system or expand it, what you basically have to pay attention for. Minh, thanks a lot for the demo.
Oh, thank you.
And I'm going to hand it back to Diep. Yep.
Yeah. Thanks, Sven. Thanks, Minh.
Oh, thank you.
So I think this is where we want to get to, right? Is you have your way. There's the last 30 years has been optimizing how people are doing HPC on premise, and how they're deploying file systems, and DDN's the experts there, and compute servers, and all these things. And in the cloud, so we're trying to get to, well, what's the best way to do it there, right? And so we really want to change some of the general dynamics around, one massive file system that you're just bin packing all of your workloads into, and really sort of thinking about how do we optimize the entire workflow where you're expanding the clusters when you need to, you're shrinking them down when they're not needed. You're targeting file systems where you can set a set of jobs for bandwidth that are bandwidth optimized, and you can set a set of jobs that are require high IOPS, and really targeting the specific needs of the applications with by doing the right configuration within Google.